Let's consider the second example. Now, in this example, we want to check whether this vector field f is conservative or not. And if it is conservative, then we should find this scalar potential function little f, so that its gradient equals to the given vector field. Okay, let's do the first part. Okay. So let's check whether this vector field is conservative or not. This is a vector field in R2, therefore we should use the cross partial test. This is your P, this is your Q. So let's calculate partial Q over partial X and partial P over partial Y. What is your Q? Your Q is x squared. Derivative of x squared with respect to the x variable is 2x. Your P is 2xy. Now we have to take the derivative of this one with respect to the y variable. Therefore we can treat 2x as if it is a constant. So we get 2x times derivative of y is 1. As you can see, partial q over partial x equals to partial p over partial y. Therefore, the vector field f is conservative. At this point, we know that we can find a scalar function little f so that its gradient equals to the given vector field. So now in the second part, our goal is to find this little f. Okay, this is the way we do it. Since f is conservative, since the vector field f is conservative, we know that there is a scalar function little f, probably with two variables x and y, little f, such that its gradient equals to the given vector field f. But what is the gradient of little f? The gradient of little f equals to partial over partial x of f and partial f over partial y. Okay, so now what was our original f? Our original f is this. So, however, the vector field f equals to 2xy comma x squared. So now if you set these two equal to each other, you will get 2xy comma x squared equals to partial f for partial x comma partial f for partial y. Okay, so this is your vector field f and this is your gradient of f. At the moment we do not know what little f is. That's what we are going to find out. So since f is conservative, we have this equation. Now I have two vectors that are equal to each other. So from this, the first component of the right hand side equals to the first component of the left hand side. So This means partial f of partial x should be the first component of this, which is 2xy. Let's say this is our equation 1, and the second component of the right hand side, which is partial f of partial y, equals to the second component of the left hand side, is x squared. So now we have two equations. In these two equations we have the derivative of f with respect to the x variable and derivative of f with respect to the y variable. Okay, so let's find our little f. So I'm going to consider equation 1. If you want, you could even consider equation 2, but here in this example I'm going to consider equation 1. Equation 1. Partial f of partial x equals to 2xy. So we know the derivative of f with respect to the x variable, and it equals to 2xy. So from this we are going to figure out little f. If we know the derivative, to undo that operation we have to integrate this, but when we integrate we have to integrate with respect to the x variable. So let's integrate both sides with respect to the x variable. So integral of partial f of partial x with respect to the x variable equals to the integral of 2xy dx. If we integrate one side with respect to the x variable, you should do the same thing to the other side. Okay, now if you integrate a derivative, then you should get the original function f of x comma y. This equals to so we can treat 2y as if it is a constant, and we have to integrate x variable with respect to the x. So then you will get 2y times x squared over 2. Now here is the interesting part. Now if you integrate something, then you need to, if you have a single variable function, then we add a constant. But now f is a function of two variables. So if we integrate some function with respect to the x variable, then maybe your constant can be a function of y. Maybe in this function we have some constants, but in general this could be a function of y, because when you take the derivative of this function that contains y variables with respect to the x variable, you will get, if you take the derivative of this function with respect to the x variable, you will get 0. Okay, so yes. Okay, now if you simplify the left hand side, you will get x squared y plus g of y. Okay. Now remember, our goal is to figure out f. At this moment we have our f equals to x squared y times some unknown function that contains only the y variables. This function contains only the y variables. Okay, so now next we need to figure out what this g of y is. To do that, what we do is we take the derivative of this equation with respect to the y variable, you will see why. Okay, so the right hand side we have partial f over partial y. This equals to partial over partial y of x squared y plus g of y. Okay, derivative of a sum equals to sum of the derivatives. Derivative of x squared y with respect to the y variable becomes x squared times 1 plus derivative of g with respect to the y variable is g prime, or if you want you could write, let's do this, dg over dy. But wait, don't we have an exact expression for partial f for partial y? Yes, we do. That's our second equation. So our second equation says exact value of partial f for partial y should be x squared. So now let's compare. Let's say this is equation 3. So let's compare equation 2 and equation 3. So let's compare equations 2 and 3, because both equations give the same thing or express the same thing. Equation 2 says partial f for partial y should be x squared, but the equation that we found for partial f for partial y is x squared plus dg over dy. If you simplify this, we can cancel this term with that, you will get derivative of g with respect to the y variable equals to 0. Now recall, g is a function of y variable only. This means g of y should be a constant. So now we can update our function little f. We can update this function. Update this function. So my f should be x squared y plus some constant. So this is the general solution of the problem. So we found a scalar potential function for the given vector field, and that scalar potential function is x squared y plus some unknown constant. We cannot find the value of this constant, but there is some constant value c. This means if you calculate gradient of little f, this function, you will get the vector field f. So in the next example, we do the same thing for a conservative vector field in R3.